Hello and welcome to today's webinar presented by Delubal Software. Today we'll be utilizing our structural analysis and design software, RFEM 6. The topic for today's presentation is building model advantages within RFEM 6. My name is Amy Heilig. I'll be your presenter. I'm the CEO of the US office and I'm located in Philadelphia, Pennsylvania. My colleagues Alex Bacon and Cisco Cho will be your moderators. They're both support engineers, also located in our Philadelphia office, and they'll be here to answer any questions throughout the presentation. We always want to encourage you to ask questions throughout this webinar. You can do so within the GoToWebinar dialog box as shown here. If by chance we don't get to all your questions, we will certainly send you a follow-up email afterwards. So we'll quickly go through the content that we will be covering over the next hour today. I do want to give a brief introduction to the building model add-on within our program RFEM 6. We'll then move on to the example structure that you see over here on the right-hand side. We'll talk about setting up this multi-story structure utilizing the building model add-on. We'll talk about how we can define stories as well as diaphragms. This will lead to load distribution discussion for our floors as well as the stiffness settings for the various diaphragms. We will be running a calculation and reviewing the results and output. And finally, at the end of the presentation today, I do want to give a summary of the advantages for the building model add-on. So for those of you joining us today that are familiar with our program RFEM 6, we do operate with this add-on concept. So this multi-story structure can certainly be modeled in RFEM 6 alone. However, we do have some advantages of the building model add-on that is available in addition to the base program RFEM. The first is to apply story-based organization. So essentially, we can take this 3D model within this general FEA software of RFEM, and now we can define stories, which again is ideal for multi-level story structures. This allows us to make quick changes to our floors rather than manually having to edit those. We also can carry out the gravity and lateral analysis together within one file. We don't need two separate programs. We don't need two separate files. So we'll see today how that can be carried out. We also can simplify the load distribution and apply diaphragm stiffness settings across our floors. So we'll discuss in great detail those two topics today within our example. Now, this is certainly possible within RFEM 6 alone, again, without the building model add-on, but we're having to manually make these modifications directly within the stiffness matrix of our floor, for example. When we do utilize both a semi-rigid and rigid diaphragm, we also have the ability to separate out what we call the 3D wall from the 2D floor calculation. And again, we'll be covering that in our example today. And finally, with the result output, with the building model output, we are now going to give you, especially in table format, story level results. So we'll be able to view shear wall forces. We can look at inner story drifts, center of rigidity, as well as story shear. This can be really important for seismic or response spectrum analysis within a multi-story structure. We also can integrate this add-on with the other design add-ons. So for example, the concrete design add-on pairs very well with the building model add-on to carry out shear wall and deep beam design. So the next question that we often get asked is when to use the building model add-on within our RFEM 6 program. So over on the left, I have some applications here that we may consider utilizing this add-on. So certainly for multi-story buildings with defined floor levels, and it really is applicable to all material types. So the building model could be used for mass timber, for example, CLT, concrete structures, steel structures, again, any material is applicable. It also can be used for regular or irregular geometry or element layout. We don't necessarily have to have the same columns and the same shear walls, that layout at every single floor. Again, irregular geometry is also supported. This can be beneficial when we have a shear wall lateral system. So we'll see in today's example how we can define these shear walls and get a nice output of the shear wall forces in comparison to RFEM alone. So structures requiring story level seismic output. So we're talking about story drift, story shear force. Again, with seismic or response spectrum analysis, this can be extremely useful. Also, diaphragm applications for load distribution and stiffness modifications. The building model add-on is going to release these different diaphragms for us: flexible, semi-rigid, rigid. Without these, we wouldn't have that quick access to the diaphragm options. And also, it is applicable for projects combining gravity and lateral analysis, again, within one model. So when is it not recommended then to use this particular add-on? For non-building structures. So if we are modeling a tank, towers, specialty projects such as art installations or an FEA of a steel connection, this clearly does not have defined floor levels, so perhaps this add-on would not be so applicable. Also, irregular vertical geometry. So I'm not talking about horizontal geometry, but vertical, when we don't really have a clear story definition. Okay, so we will get into our first example today within RFEM 6 directly. So when you do begin a new model here, you are presented with the base data dialog box. And the type of model will be in the 3D environment. The second tab within the base data is all of the available add-ons. So of course, we'll be focusing entirely on the building model add-on, which is activated for today's example. But as mentioned, it would be quite common to pair this with some of the additional design add-ons, like concrete design, to carry out the reinforced concrete design according to the ACI or the CSA standards. Steel design, timber design for mass timber structures is certainly also possible. We will be generating our load combinations automatically according to the ASCE 7, the 2022 standard, but of course, many other international standards are supported. So once we have defined this information, we are within the main program RFEM 6. And you'll notice here that I have already imported in a DXF file as a background layer. So this will just assist me with my modeling. And if we go to guide objects, and I'll go ahead and collapse this additional folder here, down at the bottom within background layers, this is where I have just imported in a DXF file directly from something like AutoCAD. You can see the elevation was set at 10 feet in height. I also have defined here some basic objects just to get our model started today. For example, I have defined already from our material library 4,000 PSI concrete. It will be a concrete structure for this example. I also have defined a couple of cross sections. So if we look at these existing cross sections, we have a couple of them, just a square cross section, 12 inches by 12 inches that I'll use for my beams, and then a circular cross section, 20-inch diameter, that I will be using for the columns, both with the 4,000 PSI concrete assigned. I also have a couple thicknesses defined. So thicknesses are assigned directly to 2D surfaces within RFEM. And the first thickness is 8 inches. This will be used for our elevated slabs. And then we also have an additional thickness of 12 inches that will be used for the shear walls, again, both assigned with that concrete material. So we want to begin modeling our structure, but before we do, I'm going to access the building model folder over on the left. And this is only available because I've activated this particular add-on. I can right click here to create a new building story. Now, this dialog box we will get into in much more detail a little bit later on, but I want to initially define my first story with a height of 10 feet. And I'm going to create 3 additional stories here, again, all with a varying height of 10 feet. So 4 stories defined. Again, we'll get back into this dialog box a little bit later to explain it. So we see those listed here under the stories. So we're now ready to begin modeling, and I will go into an elevation view here and utilize this background layer. With the building model add-on, we have some additional tool options here that are not available in RFEM 6 directly. And this is just to make our life a little bit easier when we're modeling these elements at every single story for a multi-story structure. We will begin here with defining and drawing our column elements. So we go ahead and select column from this special toolbar. And the member type is set to beam. So remember, RFEM is a general FEA program. A beam is really just any type of standard member. It could be a beam, could be a column. So we'll go ahead and leave that member type as such. The cross section for our columns, we want to toggle down to the existing circular cross section that we already have defined. Now we could additionally add moment releases such as hinges at the member ends. If I don't define anything here, everything is considered fully fixed. So we'll go ahead and leave our elements fully fixed for today. But you'll notice a special dialog box here, again, specific to the building model tools, where I can draw this column, but apply it to all stories. So all stories are activated here. And now when I zoom in to my DXF drawing grid, we can go ahead and just apply these columns by a single click here at the center of the background layer. Now, what else you'll notice is this big ball here that adjusts every time I snap to create a new column. This is the center of mass, so it detects every time a new element is added to the model and will adjust accordingly graphically. So we go ahead and assign here the additional columns at the bottom of our page. I can right click to exit out of this tool. And if I turn this to an isometric view, you can see here then that these columns were applied to every floor level. So again, these building model tools can be efficient. I will go ahead and hide what we call our member representatives graphically. Also, if the center of gravity or center of mass kind of gets in your way here graphically, we would just go to the navigator, the second tab, and also under the building model, we could go ahead and deactivate that. So going back to the plan view, we want to move on to drawing our beam elements. So again, utilizing the building model tools, we have the ability to select a new beam. And exact same workflow here as we saw for the columns, but this time I do want to select here my square cross section. I click OK, and then I am going to snap directly to the center point of my column. I right click once to exit that out. Go ahead and do the same thing here. I will be connecting these to what will be our shear walls eventually. Now, these can be thought of as collector beams, for example, transferring these lateral loads from the columns to the shear walls. And we'll go ahead and apply these beams at the left-hand side and finally at the right-hand side. Okay, so now that the beam elements are defined, those should be applied to every floor. We right click to exit, and we're now ready to draw our elevated slabs. So within my building model tools, I'm now going to access a new rectangular floor. So this is going to be a two-dimensional surface element here. I've already defined the thicknesses within the model, so we will select here our 8-inch thick 4,000 PSI concrete from the dropdown. I click OK, and then this only requires 2 clicks from left to right, and now my elevated slab should be applied at every floor. So we likely need to have some opening passing up through the center of each floor here through these elevated slabs. So once again, we have a nice feature within the modeling toolbars where I can draw a new rectangular floor opening. But this time I don't want to apply it to my top story, only to the first 3 stories. So once I have that selected here, I can go ahead and click on 2 points to apply that opening. And if I kind of toggle this to an isometric view here, you will see that those openings are now applied to stories 1, 2, and 3, but not the top level. The final modeling element that we want to apply here are our shear walls. So we will go back into the plan view, and we are, for the last time, we'll select a new element here from our modeling toolbar, such as a wall. This time we want to toggle the thickness to 12 inches. And I click OK. I'm going to zoom in here, but remember we deselected our top story. So I'm going to go ahead and select all stories again to apply these shear walls. And then I can simply snap here to my points to draw in these 4 shear walls. And I'll go ahead and close the loop here. I can right click to exit twice, and now we have our shear walls modeled. The final modeling step, though, is we probably want to add in openings here to the shear wall, maybe for some elevator, stairs, whatever it may be. So going back to the plan view, let me turn this into wireframe, and I'll go ahead and select only the front shear walls to create a visibility by the selected objects. You can go ahead and right click to deactivate the hidden objects. Now also this DXF background, if we wanted to go ahead and turn that off, we could do so within the navigator over on the left. So turning this into a rendered view, I do want to activate my drawing grid. So we will snap this drawing grid just to assist us with adding that opening here, change the orientation. And I do want to apply a new opening. And this is just going to be a standard opening tool that we find within RFEM 6 directly. So a new rectangular opening, and I'm going to snap here from my point, which is about 3 feet from the edge. My second point be an additional 3 feet, and we have our opening modeled. But a nice feature going quickly back to these modeling tools is this option to copy an object. Now, I certainly could use my Move Copy tool, which is located here in my toolbar, to copy this opening up. But with the building specific tools, when I choose the option to copy an object, all my stories are selected, and I can go ahead and click on this opening directly, and you'll notice that it replicates it up to all of my stories. The quick thing to do here for support reasons is I would like to divide this line where the opening occurs. So I'll use my connect lines and tools just to break apart that line. Okay, so canceling out of this visibility mode, we are fully done with the modeling of our structure. What we would like to do now is to apply supports at the base. So quickly doing that, we will apply new nodal supports, and we'll use the default option here as fully rigid supports. I click OK, and then I can graphically highlight over or click on the various columns here. We have one more column in the back. I'll go ahead and apply this to. I can right click to exit that tool. Now, we also want to apply line supports to the base of our shear walls. So in a similar fashion, we will select the new line support option. We'll take advantage of the default fully rigid support type. We click OK, and then I can graphically select my lines at the base of the shear wall. So visually looking at the support options, I can always right click to decrease the size of these. Maybe if I want to increase the number of supports on a line support, I can do so. Same concept here for the nodal supports. If I want to decrease the size, we can always use this slider. So now we would like to move on to some simple loading for today's example. And I'm going to go into my load cases and combinations dialog box. So remember, we are generating our load combinations automatically according to the ASCE 7 with this combination wizard turned on. I did already create 4 simple load cases for our structure today. I have defined here dead load with self-weight activated. We also have a live load, and then we have 2 wind loads. And all of these have the action category set according to the ASCE 7, as we need to know how to combine those into the load combinations. So jumping to the load combinations themselves, we can see all of our factored load combinations generated in orange and all of our unfactored load combinations generated in red. So now that those load cases have been defined, we need to actually apply the loads to the structure. So we can jump here to our dead load, And again, for today's example, very simple loading applications, we will just apply a new surface load for our dead load. And the load magnitude here is going to be set at negative 0.05 kips per square foot in the global z direction. And then I can graphically select my surfaces to apply this gravity load. So I'll go ahead and use my selection box here to highlight surfaces 1 through 4. If I click apply and next, I remain in this dialog box, and you'll notice in the background, these loads are applied to the structures. The openings are also considered at the lower floor levels. But this also allows me then to toggle simply to live load. I can modify the load magnitude here, negative 0.075 kips per square foot, and I can directly type in surfaces 1 through 4 on my keyboard, and I click OK. So same concept here for live load. Now, for my win load cases, I did want to make it known that we do have a load wizard. So we could generate these win loads automatically according to the ASCE7. The structure is perfect for it. It's a rectangular type shape. We can generate load cases 1 and 3 according to the ASCE7, or if we had a rigid diaphragm, load cases 2 and 4 in addition to that. There's also a snow load generator. So I encourage you to check these load generations out utilizing the load wizard. But for today, again, very simple example that we'll just manually apply these lateral loads. So for our first win load case, I'm going to apply a new line load. And this is not to be confused with what's right next to it, a new member load. A line load would be applied directly to surfaces. So choosing a line load option and modifying the magnitude here of negative zero point 0.2 kip per feet, I am going to apply this in the global y axis. And we can see our axes here in the background. And then I will graphically select the lines where this lateral load will be applied. Again, clicking the apply and next, it is applied in the background here, where I can now toggle to my second win load case. And to simply apply this to our line elements over on the right-hand side by clicking on them. And we also want to change the load direction to the global X, and I can click OK. So now we have that additional lateral load for our fourth load case. If you're interested to see these load combinations here applied to the structure together, we can do so by jumping to one of the load combinations. If the display looks a little bit too big, we can always right click and use our slider here too. Taking a look at load combinations that include the lateral load, we can see that displayed on our structure accordingly. All right, so we want to get back into these building specific features within the building model add-on itself. And the next thing that I want to do within the building model folder here is to define our shear walls and deep beams. So we will begin first with defining a new shear wall. And before I do, I will turn this to an elevation view. Maybe just to mention, there are defined visibilities here with the building model add-on. If I quickly wanted to access only a particular story, I can go ahead and turn on those automatically created visibilities. So just keep that in mind that that is available. But for me, I'm going to go to a plan view here, and we'll go back into a wireframe. And I want to select only a couple of shear walls. Now, realistically, we would probably be defining, of course, all of our shear walls. But for today's example, let's just focus on these two. So going back to our building model folder, we can right click here to create a new shear wall. And the first shear wall will be defined by directly clicking on the surfaces over on the left-hand side. So pretty basic application here. I can directly select the surfaces. You'll notice that the layout is identical at every floor, so therefore we can select them all at once. Now, shear walls do not necessarily have to be in a single plane. They can be L-shaped, they can be U-shaped, they can be box-shaped. Really, anything is possible, but we will just keep this one as a simple application for today. The other thing I want to mention too, I talked about pairing this with the concrete design add-on. So if the concrete design add-on was active, we would have the ability within this dialog box to directly define our reinforcement. But I didn't activate that add-on for today. We certainly have previous webinars where we do combine these two, so you can refer to that if you are looking for more specific concrete design workflows. Now, that first shear wall is complete. The next shear wall poses a bit of a problem because we have this extremely large opening here that if I were to define the shear wall by directly clicking on these surfaces, the result output will not be correct because we're trying to sum up these forces uh, within a very simplified table output. And when we're talking about moments and things like this, it just wouldn't be accurate with this very large opening. So instead, we can define shear walls with what we call surface cells. And that's the visible display here as a surface cell, but this will make more sense in a minute. We need to create the surface cells when we have applied a standard opening to these surfaces, and we have a nice tool in RFEM that will quickly do that for us. So I hold down my control key, I select all surfaces, and we have the ability to create the surface cells due to openings based on the local y-axis of the surface. So when I do that, and I'll turn this maybe into wireframe view, these surface cells are generated at the left of the shear wall, the right of the shear wall, and at the top. So you can see those three separate elements here. This will now allow me to define my shear wall at the left, at the right, and then I can define here what we call a deep beam. So otherwise known as piers, as well as our spandrel. But when we have these openings, it's not so easy to detect those when defining the shear wall itself with a standard surface. So creating yet again a new shear wall, this time I'm going to graphically select the surface cells on the left spanning from top to bottom. I'm going to create another definition here for a third shear wall where we will select these surface cells on the right. And I click OK. So those shear walls are now defined. And I want to move on to defining here what we call our deep beams or our spandrels. So I create a new deep beam definition. And I want to go ahead and select my surface cell that was created here at the top of my opening. I'm going to go ahead and create separate deep beam entries here for each one of these surface cells. And we'll do it for a third time at the third surface cell here. And finally, we have one more deep beam option up here at the top. Okay, so now all of these particular deep beams have been defined and we can click OK. Again, if we paired that with the concrete design add-on, we would also see reinforcement options there. So what is the shear wall and deep beam? What would be the benefit? Well, right now we have these two-dimensional surfaces here, right? But by defining the shear wall on top of that, this overlays what we call a result beam, where result beams are going to integrate or sum up all the stresses and forces from surface number 17 and present it to us in more a one-dimensional format. So we're going to be able to see the total axial shear forces, bending moments of this wall presented in a much better format than a 2D surface within this general FEA program. So now that the shear walls and deep beams have been modeled and defined, we want to go back to the building stories. And I'm going to right click here. If you remember, this was the dialog box that we were initially in to create our 4 different story definitions. So let us dive a little bit more into some of these various settings. You'll notice that I can toggle this view over here on the right-hand side. And as I click on each story, the program shows me a nice view of all the elements that are tied to that particular story. We also have defined here the height for each one of them as 10 feet. Now, this is all related to diaphragms. We will get into this in just a minute, but I'm going to go ahead and take a look at the global settings to explain these options further. The first is what is the ground level elevation so that we can begin our first story. This is set as 0 feet by default, but perhaps if you are modeling only upper stories of a structure, you could modify the ground level elevation here. The story height modification. So there are 4 options here. The default option is no selection. So we just kind of have this dash selected here. What this means is that if I go back to my story definitions and I tell the program, okay, let us go ahead and modify the first story to 15 feet. And I click OK, what you'll notice happens is that nothing is modified within the RFEM model itself. But now we have this story definition that kind of lands right here in between my stories. So it's again not affecting the RFEM model directly, but rather just the story height definition. So we'll go ahead and change this back to 10 feet. But the other options include fixed to top, fixed to bottom, or proportionally. So what these options are referring to are any intermediate nodes between stories. And perfect, for example, today are these intermediate nodes for our openings on our shear wall. If I were to select here fixed to bottom, for example, and I go and modify that story height to 20 feet, well, fixed to bottom means that it will add an additional 10 feet to the top of this shear wall and this story itself. Fixed to bottom means that it will go ahead and, sorry, it's kind of opposite. Fixed to top means it will keep these elements the same and add the 10 feet to the bottom of our story. Fixed to the bottom will go ahead and add that additional height to the top of the story, and then proportionally we'll tell the program to essentially apply 5 feet at the top and 5 feet at the bottom. So let's take a look at what exactly this will do. So we'll go ahead and choose the fixed to bottom option. I'm going to go in here and edit my first story level height to 20 feet. And we'll go ahead and click OK and see how this affects our RFEM model here. So within this RFEM model, you'll notice that the first story height is modified within the RFEM model itself, not just with the story definitions. And because we have this fixed to bottom, it has applied an additional 10 feet here above those intermediate nodes. So essentially that's how those different options will affect our structure. Now we'll go back to the building stories here. We want to modify this, of course, back to 10 feet, and the global story height modification settings, we'll just change that back to nothing. The story height definition, this is just initially set to effective height, which means it's going to measure the height from the center line of the slab to the line of the upper slab. Alternatively, with a clear height, we have the ability here to define a slab thickness, and this height will then be measured from the base of our structure up to the bottom thickness of the slab element. So if I put in 1 foot here, for example, the height would be from the bottom to the bottom of the structure to the bottom of the 1 foot thick elevated slab. Show warning for neglected openings. So this is what I was talking about with something like the shear wall definition. So if we have these extremely large openings or any opening larger than 10% here by default of the total area of the surface, and we go in and try and define a shear wall just like what we did previously, the program will give us an error. It will say, wait a minute, you have a pretty large opening, so the output of your shear wall forces may be incorrect. So therefore, we want to look at something like surface cells, or maybe we want to model each of these as separate surfaces. That's also a possibility. The vertical result line, this will certainly make more sense once we actually run the calculation, but this is a vertical section for a result diagram that will be displayed graphically within our results. And this is just simply related to where do you want to place this vertical result line graphically? Do you want it set as a percentage here, which refers to the center of mass in the X and Y directions? Or do you want to toggle this off and just simply set this distance in feet from the origin point in the X and Y directions? The final one is calculate center of rigidity. So this one's very interesting in the fact that whether you have no diaphragm defined or any one of the other diaphragms defined, flexible, semi-rigid, rigid, we will always calculate here a center of rigidity when this option is turned on. And we know the center of rigidity is a point at each floor where applying a lateral force causes translational movement only, but no rotation. And we typically determine the center of rigidity with something like a rigid diaphragm only. But in RFEM, it's entirely possible to determine the center of rigidity for all other diaphragm options or no diaphragm at all, because internally we are going to convert our floors with a rigid in plane stiffness in order to determine that point. Now, this does not affect the analysis. We're not going to apply a rigid diaphragm for a flexible. It is purely just used to calculate the center of rigidity only. If you want to turn that off, you can go ahead and do so. All right, so now we're going to get into the diaphragm options. And within our drop-down box here for each floor, we have 4 different options for diaphragms, either none, semi-rigid, rigid, or flexible. So let us go back to the PowerPoint to discuss this topic in more detail. So we might be wondering, well, when would we want to model a diaphragm within our RFEM 6 file versus maybe not defining a diaphragm at all? So within this table here, I have listed the 4 diaphragm types: rigid, semi-rigid, flexible, and then no diaphragm at all. So starting first with the rigid diaphragm, this is typically recommended here for floors that have that are made up of concrete flat plates or slabs. Perhaps you have some type of composite deck with a thick topping, where ultimately what we want within the diaphragm behavior is rigid in plane stiffness, where we distribute these forces to lateral walls and frames. But what we don't want is any out of plane flexural stiffness of our floor contributing or polluting the lateral stiffness. Now, in a similar manner, we also have here our semi-rigid diaphragm. So this might be used for concrete with significant openings. Perhaps we have a deck with a very thin topping. It also can be used for mass timber, but I do want to specify here, if you're modeling something like a CLT floor, it should be one continuous surface. If you are modeling with the joints behavior, so I'm talking about line hinges where we release the moments and we account for the slip of the connections, I would not recommend a diaphragm at all. So basically mass timber, CLT, if you're not modeling those joints in detail. For semi-rigid, we want the true in-plane stiffness to distribute the forces to the lateral walls and frames. So rather than a fully rigid, we want the true in-plane stiffness to be used in that in-plane direction. But similar to a rigid diaphragm, we do not want the out-of-plane stiffness to contribute to the lateral stiffness. The third diaphragm type is flexible. So this might be used for something like a floor made up of wood panels, such as OSB or plywood, or we have a bare metal deck, where ultimately we want this floor to distribute the loads based on tributary area only. We do not want any in plane or out of plane stiffness contribution from the floor itself. The final option is no diaphragm at all. This would be recommended again for something like mass timber with those CLT panels where we are modeling the joints with those line hinges. But realistically, no diaphragm can be applied to all materials because if you want to account for the true in-plane membrane and out-of-plane bending stiffness for load distribution, that's what this none option would allow you to do. So basically, it would be applicable when the diaphragm behavior assumptions are simplifying the true floor stiffness. And this would be a general FEA approach. So we want to turn now to the different diaphragm types and stiffness applications within RFEM itself. So once again, we have this table here where I want to clearly lay out the diaphragm stiffness for the 4 different options. And we'll start first with the diaphragm types rigid and semi-rigid. The reason why I'm grouping these together is because within RFEM, when we assign these diaphragm types, we will carry out 2 separate calculations. We will always split this up. The first is what we call the wall's global 3D calculation. And this is essentially where we are going to modify the stiffness properties set by this diaphragm type to distribute the loads. So we're going to take this full structure here. And for example, a rigid diaphragm will go ahead and set the out of plane stiffness to 0. The in plane stiffness will be set to an infinitely high number. We are going to apply both lateral and gravity loads to receive our results. Now, we also carry out a second calculation, though, where we extract each individual floor into a separate model that goes on internally within the program. And we're going to use the true out of plane and in plane stiffness for these floors. So no longer are we simplifying with the diaphragm types. And everywhere where we have a column framing in or a shear wall, this is where we're going to place these support conditions within that submodel. So we extract out this model internally for only this single floor. We support it where we have any elements framing in, and we'll go ahead and apply the loads, which end up being gravity loads only. This will make a little bit more sense once we get to our example. So this is purely a gravity load analysis for our floor design. This one, I'm hesitant to say it's only lateral design because we are still applying gravity loads too, but we are applying the simplifications here set forth by the different diaphragms. Now for semi-rigid, exact same concept. We still carry out two separate calculations. The out of plane stiffness for our global 3D calculation is set at 0, but the in plane stiffness is the actual stiffness based on materials, the thicknesses. And again, we carry out that separate 2D floor calculation as well for semi-rigid using the actual stiffness for both in plane and out of plane. Now, for flexible and none, I group these together because we only carry out one global 3D calculation. We're not going to separate this out into floors versus walls here, but rather you can kind of think of it like a general RFEM 6 FEA approach where we just have one calculation. We apply both gravity and lateral loads. The difference here with the flexible is that we set the out of plane and in plane stiffness to 0. So it's going to be used for load distribution only. And then with no diaphragm defined, again, general FEA approach, we use the actual stiffness for both in plane and out of plane based on materials, thicknesses, and so on. So going back into RFEM, let us take a look at applying these different options within the program. So you can see by default that the floor diaphragms is set to none within this dropdown. So no diaphragm simplifications will be applied in this initial case. And if I jump down to something like my dead load and I display my loads here, what essentially will occur is the load will be applied and distributed to all elements just purely based on FEA. And this is true for gravity, for lateral, everything is applied together in these different load combinations. So nothing necessarily so unique here. But going back to the building stories, if we highlight all 4 stories and let's change this to a flexible diaphragm only. So when we click OK and we go back into the RFEM model, and you can see here this created floor sets, I'm going to go ahead and turn that off graphically. We're still looking at this dead load case. And what you'll see now when I double click on my floor is that the stiffness type went from standard to what we call load transfer only or flexible diaphragm. I can't change this, it's grayed out because it was set directly within the building model add-on. So within the calculation, again, no in plane or out of plane stiffness will be used within the stiffness matrix of this particular element. Rather, it is used for load distribution only. So under the second tab, we can see the different options for these load distributions. Now the default here is going to be FEA. The other 3 options are just simple tributary areas only. So we either have one-way area load distribution or two-way area load distribution. Uh, Circling back here to the FEA option, which again is set by default, what this does is that internally, this surface will be considered to a rigid, will be converted to a rigid element. And everywhere where we have a beam, a column, a shear wall framing in underneath it, we replace it with a rigid support, whether that's a rigid nodal support or a rigid line support. We determine the reactions from this submodel, and those reactions are essentially what we use to now distribute the loads to the structure. So if we leave this at the FEA option here and I click OK, and we're just looking at a dead load only, I'll go ahead and run a quick calculation. Now, if I did try and run a load case with a lateral load too, I would get an instability because I don't have any lateral stiffness to my structure. Otherwise, if this was a flexible diaphragm, but for this gravity load only, we should be able to see what this load distribution and results look like. So we'll cycle through a couple of calculations. The first is to determine the load distribution, and then the second is to actually run the analysis within RFEM. So what we'll see here is our results. I'm going to go ahead and turn off the display of my FE mesh, and under my viewing options at the project navigator, if I expand here all the way at the top under my surfaces, I have the ability to convert these loads to load transfer surface to see exactly how they're going to be distributed. So again, this is what the program is doing internally, and I'll go ahead and create a user-defined visibility here for only these elements with the FEA option. So very detailed here in how these loads are going to be distributed to the objects. If I double click on this floor and I modify this load transfer option to, let's say, X and Y stripes, and I click OK, it's telling me I need to clear my results. We don't need to run the calculation because it's all just based on analytical tributary area, but you can see how much more simplified this looks by just considering basic tributary area over the FEA option. So turning this back to the FEA option, by default, we can go ahead and cancel out of this visibility. So I do think it's important to explain here how these loads are applied when we modify the diaphragm type to something like a flexible diaphragm. So let us go back to the building model add-on, and I'm going to change all of the diaphragms now to the type rigid. Now, semi-rigid and rigid, again, are very similar, so we'll just continue on with a rigid diaphragm for today. What you will notice is that these options listed below are now going to be applicable for the semi-rigid and rigid diaphragm. And these are specific to that local 2D floor calculation I was talking about in the PowerPoint. Remember how I mentioned we will extract each floor out of the model for this 2D calculation, and we use the true in-plane stiffness and out-of-plane stiffness for the floor analysis and design. Well, I had also mentioned that everywhere where we have a column framing in or a shear wall framing in, we need to support that within that local 2D model that's kind of going on underneath the hood. So these are the two support options available. Now, the default is just a simple hinge support for both a nodal and those line supports. But within this drop-down box, you can get pretty detailed in terms of how that 2D floor element is supported. So for example, we have elastic columns where you can define, okay, is this column hinged or rigid at the base? Is it hinged or rigid as it's framing into the surface? And the program knows the material, it knows the height, it knows the dimensions. So therefore it can calculate the true stiffness of this column framing in here to this slab and apply what we call a spring constant here for our nodal support. The exact same concept here for line supports for walls. We can get a little bit more detailed rather than a general hinge support. Now, the members included within this local 2D calculation, if I had elements that were members, beams that were gravity only. So, for example, at these beams, kind of spanning between the columns to shear walls, if I wanted to consider them for gravity loads only and not for any lateral loads, I would input them in to this option here by graphically selecting them or typing in the numbers. Now, when I leave this empty, this just means that these beams will see both gravity and lateral loads within that global 3D model. Okay, so once we click OK, because we have gone through all of those details here, what you will notice is that the program does place here what we call these rigid links to represent the diagram, or sorry, the diaphragm graphically. We can go ahead and turn off the rigid links graphically here within our navigator once again, if that does seem to get in your way. Double clicking on my floor surface here, what you'll notice, the stiffness type was automatically updated to a rigid diaphragm, again, set directly within the building model add-on. Looking at the load transfer, we have the same options here that we previously covered. So we can go ahead and drop down to one of our load combinations that has both gravity and lateral loads to run a quick calculation. Now, for this calculation, it will go ahead first. The first calculation that you're seeing is to go through the load distributions for the dead load, the live load, and the wind load, because we have that set to that FEA approach. Then it's going to run through the three additional analyses here for this load combination. The first is going to be that global 3D model where we make those diaphragm assumptions. But then we're also running a second calculation where we extract out this floor to use the true stiffness properties. And the third calculation is going to be for the center of rigidity. So that's why you see three separate calculations going on here for this load combination. So now that our results are complete, what we could do here is to take a look. I want to start off with first the table results. So I'll go ahead and turn off the display of the results now graphically, and we jump directly to the table. Well, within the static analysis, we have the results by stories available to us. This would not be available otherwise if I did not activate the building model add-on. So this is why, regardless of diaphragms and anything of the sort, it's a really nice output for each story of our analysis data that otherwise we wouldn't get within RFEM 6 alone. So we can view here the center of mass that's shown graphically as well as the coordinate points, but we're also getting the center of rigidity. So you can see that's slightly offset due to that large opening, and that is given at each of the four stories. We also are given what we call the story actions. This is going to be the story shear force. So we can see the shear forces in the X and Y directions for each story. This would be important for something like seismic analysis. Same thing with drifts. So we give you each drift here in the X and Y directions as well as rotation at each story. And finally, we have those shear walls. So remember, we defined here our shear wall, our one continuous kind of shear wall passing up over on the left here. Well, each surface is now presented to us in table format. So we've summed up the internal forces of this 2D surface, and we give you a nice table presentation here of the total axial force, the total shear force, bending moment. You can export this to Microsoft Excel at the click of a button here. Of course, we could take this information further into our design add-ons as well. So a nice output there for the shear walls as well. Uh, the results that we want to jump to now is the graphical display. So when I turn this on, and remember for a semi-rigid and rigid diaphragm, you will have this new option here within our results navigator where we can view the results of the global 3D calculation versus the local 2D calculation for those individual floor elements. The third option here is to combine both of them graphically, but two calculations were carried out. So initially you'll notice the global deformation. I currently have this set to the global 3D model, but I think what's going to be most telling in this situation of this 3D model, remember we have a rigid diaphragm. So this is where we've set the in-plane stiffness to something infinitely high. The out-of-plane stiffness is set to 0 at our floor, but all other elements are active for the applied gravity and lateral loads. Well, looking at the surface results themselves, and I'm going to go ahead and just activate here my top floor only. And I'll go ahead and display here the hidden objects so we know exactly where we're at. You'll actually see within the surface results and the internal forces, mx is equal to 0. My is also equal to 0. That's because we do not have any bending stiffness in the out of plane direction. Vx and Vy are also 0. But when I toggle this to that 2D floor calculation instead, remember we're now extracting out this floor so that it's a single element. We're supporting it at the column and wall locations. I actually do see internal forces for MX and MY, those bending internal forces. That's because we're using the true stiffness properties from this 8-inch thick concrete elevated slab. And we're going to apply these loads to it again. Again, lateral doesn't really matter here because we've now supported it in this submodel at each of these locations. So we can take lateral out of the equation here, and we're now applying only those gravity loads to design our floor directly. What else we can take a look at is our member results. So we'll go ahead and turn off the surfaces and let us cancel out of this visibility mode. And if we look at the global 3D calculation, we can activate the member forces. For example, the axial forces. I think this is a topic worth mentioning here. I'm going to go ahead and try and create a visibility only based on my first floor. So looking at my first floor only, nope, I didn't capture my members. Give me 1 second. I want to capture both the floor as well as the members, but I'm trying to also not capture the deep beam. Okay, so looking at the visibility by the selected objects, you do have axial forces within these collector elements. So I know that this is a topic that is discussed in other software, that when we have something like a rigid diaphragm, we actually end up bypassing the collector beams because these lateral forces go straight from the columns into the shear walls because only every node is essentially connected to that rigid diaphragm. But RFEM is still applying FEA principles for all of these calculations, meaning we still use the stiffness matrix for this floor element, but we go directly into the stiffness matrix and we modify the in-plane stiffness and the out-of-plane stiffness, but yet we're still using the FEA approaches here. Therefore, these forces are collected in the slab element and they are transferred to these collector beams. Now, we also can view bending moments because this isn't just lateral loads being applied to the members in the 3D model. We're also applying those gravity loads that we talked about too. We can see them applied here within the model. So we will have these beams designed for the gravity loads as well as the lateral loads. The final thing to mention graphically is to go ahead and display, if you remember, the vertical result line. So within the vertical result line, I'll just leave everything hidden for now so that you can see this. This is what we set the location to in the building stories dialog box. So this is just a nice format here showing you an elevation view of the results of our entire structure. So within the entire structure, we can go ahead and activate here what is the shear force of this building. So we can see that the shear forces increase, of course, as we get to the base of the structure, but graphically shown here how those vary at each story level. We can also view the deformation in the X direction. And as we would expect, we have higher deformations at the top here, again, due to those lateral loads. So this is just a nice output as well, kind of summing up all the internal forces of our structure and presenting it by each story. All right, so that will conclude our example today. I do want to go back to the PowerPoint here to kind of sum up the building model advantages that we saw today, but also mention a few more. So to begin, you can see how both the gravity and lateral analysis can be carried out within one file, one model. And we have the ability to automate this diaphragm behavior for both the in plane and out of plane Stiffnesses. And in the case of the semi-rigid or rigid diaphragms, we will go ahead and separate out the analyses into that 3D and 2D for our floor design versus all of the other elements taking those additional lateral loads. Now, as I mentioned, RFEM is still an FEA-based solution, right? That ultimately, this is a very powerful program applying FEA principles. So when we talk about diaphragm irregularities, large openings, this is entirely possible within the program and the building model add-on. This is not affected like what we would see in other software because FEA is used underneath the hood. And with that, we have full control over the diaphragm meshing. So we can automatically set a larger mesh as we see over here on the right-hand side, a smaller mesh. We can add in FE mesh refinements at locations where we know we have higher stress points and we want to refine that. This is all possible. We talked a little bit about those beam collector forces being captured. So again, we are directly modifying the stiffness matrix of the floor element, but still applying FEA. Therefore, the force flows through the slab mesh and those collectors do pick up those axial forces, whereas in other software, we may see them bypassed. We also have the ability to exclude beams from the 3D analysis. We talked a little bit about that with the semi-rigid and rigid diaphragms. If we want to essentially exclude any beam members from those lateral loads, we could do so and apply them only to that local 2D model. Now, we didn't get much into this, but for the design of transfer slabs, or if we're just trying to get more information about our cords and collectors and evaluate these forces after the analysis, we have some great tools in RFM, such as result sections, result lines and beams. These are hyperlinks in the PowerPoint that is attached to this go-to webinar that will take you directly to our website to talk a little bit more about these useful tools. Again, of course, didn't have time to get into that today for the actual diaphragm design or the floor design, but you can certainly reference those. And finally, slope diaphragms. This is a very common question. Can we do slope diaphragms? So I would suggest that the building model itself, we don't define slope diaphragms. But within the base program RFEM 6, this is entirely possible. And we could certainly combine standard horizontal diaphragms with slope diaphragms with both the building model add-on within RFEM 6. So in the base program, we have a surface stiffness type called load transfer surface only. So basically, this could be used as a flexible slope diaphragm if you wanted. But also, we have a rigid link diaphragm directly in this base program for something like a rigid slope diaphragm. Again, these are hyperlinks to discuss a little bit more about those options. All right, if you liked what you saw today with the building model add-on RFEM 6 or interested in any other capabilities, we would love to connect with you. You can scan the QR code here. Our email address and phone number are shown at the bottom of the screen, and this goes directly to our Philadelphia office. I would love to get you set up with the 90-day trial version. It's full capability. It includes all add-ons, including the building model. We will have many more upcoming webinars. You can register at delubel.com under support and training webinars. As most of you know, I tend to send out a reminder email before these take place, so you can register directly through email. We try and do them approximately once per month, so keep an eye out within the next month for an upcoming webinar. PDH certificates will automatically be emailed to all participants who are here for the full presentation. So this is a requirement of the states that we are pre-approved providers, that you're here for the full 60-minute duration in order to receive that PDH. If you watched with a colleague or you watched in a conference type setting and you yourself did not register through GoToWebinar and you are wanting PDH, please send us an email requesting that to info-us@delubel.com. Let us know who you watched it with, ensure you were here for the full duration, and we'll be happy to issue that. PDH is not automatically issued once this webinar ends. It does usually take us about a day or two to get that together, so just keep an eye out for that within your email. And with that said, I want to thank everyone for attending. There will be a very short survey. We would really, really appreciate it if you could take the time to just answer a few questions there, help us improve our webinars. And with that said, I want to thank everyone, and we hope to see you at the next presentation.